In this next lecture on memory, we will be focusing on memory management. In particular, we will be looking at the concept of virtual memory and page-based systems. So this is sort of a bare machine view. This is our data path that we've been looking at earlier in the semester. Um, we have all these blocks that correspond to, say, for example, if I start all the way to the left, I have a program counter over here, followed by instruction cache, a decode block, an execution block with an ALU, and a data cache, which is part of the memory. And all these green rectangles over here, those are corresponding to the inter stage pipelining buffers. So that's for the decode, for execute, memory, and write back. Now in this data path, what we have is two aspects that belong to the memory, which is the data cache over here, or the instruction cache, which is at the beginning. Now because the CPU interacts with the cache first, that is the layer that we look at to begin with. And we would need a memory controller that facilitates those addresses to make sure that the access to the instruction cache and the data cache can take place. But that is going to be communicated through a physical address location. That physical address is the same address we would need to interact with the main memory, the dynamic RAM. Now, if we look at all the addresses on this diagram, they are all physical addresses, which means these are real addresses. And a problem, a consequence of that could be the fact that we would have limited number of physical addresses, because it's a limitation on the number of bits. Or it could be the problem could be many-fold. So let's see what problems we have to face because we only talk in terms of physical address. So we come to problems with memory. Well, the first problem that could happen is we probably don't have enough physical main memory. So this is the RAM that we often talk about. Nowadays we talk about a 4 gig RAM or a 8 gig RAM. That might not be sufficient if we just have physical addresses. So for example, if you have several programs that are residing in the RAM currently, and it could happen that we might need, say, 4 gigs of RAM, but we only have 1 gig of RAM right now. Later on in this lecture, we will see how that might be a very reasonable thing that could happen. So if we have 1 GB and 1 gigabyte, and we need 4 gigabyte for my programs to execute, then I'm short of memory. So I'm going to have a crash because of that. The other problem that could happen is, how are we going to share that limited physical main memory between all those several programs, because they all need to reside in the same place? Well, if we are executing programs in a particular order, we are going to bring things in and out of memory depending on which program we are executing, and that could lead to holes in the dynamic RAM. And if we try to bring in new programs that do not fit into continuous holes, contiguous blocks of memory, then we have a problem over there as well. Now, the third problem that could happen is, what if there are multiple programs that are trying to access the same physical address? In this case, data corruption could occur, because the different programs are trying to write to, for example, the same physical address. Then of course we are going to have data corruption. And it is a problem because we do not have a mechanism to separate those the memory for the memory they access. And a key problem in all of these points is the fact that programs access the same physical memory in the dynamic RAM. So a solution could be each program gets its own virtual space or virtual memory. So that is a very useful alternative that we are going to look at in this lecture, virtual memory. In general, memory management of a computer has three orthogonal or independent functions. One is translation. That translation means translating a virtual address into a physical address. So trying to map a virtual address to something that is real, physical address. That's one independent function. The other one could be protection. So do we have permissions to read, write, or read and write a word in memory? The third aspect of memory management is managing the virtual memory. Virtual memory is essentially a transparent extension of our physical memory space, in which we are essentially using a slower disk storage. So a virtual memory is sort of a cache to the RAM, so that we do not access a slow hard drive. And we will take a look at that virtual memory concept a little bit more. Most modern systems provide support for all of the above functionality by using a page-based system. A page or a memory page, let's write that down here. A page is the same as a memory page, also called as virtual page, is essentially a fixed length contiguous block of virtual memory. So fixed length contiguous block of virtual memory. We'll take a look at some typical sizes in a little bit. So pages could be several kilobytes, depending on the application. So we are going to look at paged memory systems over here. A processor or a CPU generated address when interacting with a page-based memory system has two parts. It has a page number and it has an offset. They are going to give us two different the reason for a page number is different from having a page offset. The reason for a page offset is the location difference between the byte address we want and the start of the page. So we would need enough bits in the offset to be able to get to any byte in that particular page. So that's why we need a page offset. And we have a table over here that essentially maps virtual addresses to a physical address. So in this particular diagram over here, on the left we have a virtual address space for program 1, and we have a page table that essentially maps the virtual address space to a physical memory space, and that is specifically for a program 1 in this case. Page tables for programs are disjoint, they don't overlap, so every program gets its own page table. And on the rightmost over here we have a physical memory, and as you can see, The page table seems very organized. The virtual address space seems very organized and continuous. However, the locations in the physical memory are sort of messy and you know giving us a flexibility. We are going to see that actually benefits us. So over here, if you look at this virtual address space, it has a mark of 0, 1, 2, and 3. Those are my page numbers. So page 0, page 1, page 2, page 3. And those pages are going to be mapped to different locations in the memory based on what we have in the page table. So page tables over here they make it possible to store the pages of a program, in this case program 1, in a non-contiguous fashion. They don't have to be all 0, 1, 2, 3, for example. I can have this page 0 over here, page 1 over here, 2 over here, 3 over here, and I have some free frames in the physical memory in which I could have another program residing. So that will allow me a lot of flexibility when it comes to using the same physical memory for various programs. Now let's take a look at 3 different programs. Over here we have program 1, 2, and 3. They have their virtual address space 1, 2, and 3 highlighted in different colors. Each program gets its own page table. For each page number in the virtual address space, there is a corresponding entry in the page table for each program. And all the way to the right, we have a physical memory space, which is essentially going to be dictated by our dynamic RAM. So physical, and it's a real memory. Some of the space in the physical memory could be occupied by the operating system. Some of it could be free, and some of it could be occupied by non-contiguous pages from different that correspond to different programs. So each program gets its own page table, and if we need to look up a particular page table for that translation, so we have a virtual address over here. Let's see, let us write the virtual address incomplete. Virtual address over here. We look up the page table, and essentially it gives us a physical address so that we can access somewhere in the physical memory. And there could be some frames in the physical memory that are essentially holes. They don't have anything over there. Now in this particular diagram, if you notice, each physical address location is unique. There is no overlap. That does not have to happen necessarily, because if two programs are sharing information, sharing some data, in that case the same different virtual addresses could point to the same physical address if there is sharing. So having a different page table for each program allows us to facilitate even that. In this case, we are just showing that there's no sharing going on. It's the operating system's job functionality to ensure that all the page tables are going to be disjoint. You might wonder where these page tables reside eventually in hardware. Where do they reside? All the page tables actually reside in the dynamic RAM. So that's the main memory. They reside in the main memory. So they are part of the physical address, physical memory. All right. So let's see how that translation works in a little bit more detail. So our goal is to map from a virtual to a physical address. On the top we have a virtual address, on the bottom we have a physical address. Both these addresses have a page offset, and we talked about why we need that page offset. That's going to be the offset from the start of the page to the location that we are trying to access. In this particular case, we have a 12-bit page offset that does not need to be translated. It goes straight down to the physical address. It's the same 12-bit physical address that corresponds to it. Now, because we have a 12-bit page offset, that means that our page size is going to be 2 raised to 12. So that will be that will work out to be 4 kilobytes. So the page offset, the number of bits in the page offset field determine the page size. So each page, the size of each page is going to be 4 kilobyte in this case. Next, let's take a look at how many bits do we have in the virtual address. We have starting from 0 to 31. So we have a 32-bit virtual address space, and we have a 30-bit physical address space, and 12 bits in each of those address spaces belong to the page offset. Now, using this, let's try to calculate the number of pages in a number of physical pages. So how many physical pages are we going to get? Well, for that I need to know how many physical page numbers do I have. I have starting from 12 all the way to 29. That would give me 18 bits. So 18 bits means I have 2 raised to 18 physical pages. The reason is we have 18 bits for physical page number. Next, let us see how many what is the size of the virtual address space. The virtual address space, because it's a 32-bit virtual address space, our virtual memory is essentially going to look like 2 raised to 32 bytes, which comes out to be 4 gigabytes. And my physical address space is going to be it's a 30-bit physical address space, so that's going to evaluate to a 2 raised to 30 or 1 gigabyte RAM. So as you can see, we are giving an illusion that we have 4 gigabytes of RAM, when in fact in reality we have only 1 gig RAM. Now, in terms of page size, we said it's a 4 kilobyte. That's a very typical value. Page size pages should be large enough so that we can reduce the high access times. Typically, 4 kilobyte or 16 kilobyte is a good size for a page typically. However, it really depends on the kind of application. So for a bigger application like desktop or server systems, we would need a higher page size. So maybe a 32 kilobyte or even a 64 kilobyte. For smaller applications, so for example for embedded systems, we would probably need a 1 kilobyte or smaller page size. Alright, let's move to the mapping between a virtual page number and the physical memory, or sometimes we might need to access the secondary storage, which is the disk storage over here. This slide has a virtual page number all the way to the left. We are seeing a page table in the middle over here, hopefully for a particular program. And all the way to the right we have things that are absolutely real. So physical memory in your main memory, which is your dynamic RAM, and then your hard disk storage over here. Each program gets its own page table, and that table is stored in the memory, as I pointed out. The location of this page table in the memory is stored via hardware or software in a special register called a page table register. Now, what does the page table allow us to do? Well, the page table essentially maps each page in the virtual memory, and we are going to have to know what that page number is to know the index here. It's going to map that page in the virtual memory to either a page in the physical memory or main memory, or a page stored on the disk, which is essentially the next level in the memory hierarchy. The virtual page number is used to index the page table, and at that particular entry, at that particular index, if the valid bit is on or 1, the page table is going to supply us with the physical page number, that is the starting address of the page in memory, corresponding to that particular virtual page. So we are able to access it. If the virtual bit valid bit is off or 0, the page currently resides in the hard disk at a specified disk address. So this particular page table either has a physical page location, physical page, or a disk address. Now, in many systems, the tables of physical page addresses and the disk page addresses, while logically one table is enough, they are stored in two separate structures. Dual tables are justified in part because we must keep the disk addresses of all the pages even if they are not in the physical memory. Note that the pages in the main memory and the pages on the hard disk should have the same size. So the page size remains the same for a page-based system all across the board. Now let's take a look at the virtual memory address. Over here we have a virtual address space. We are showing capital M number of pages, page 0 all the way to page M-1, and this could be just for one specific program. This is supposed to be, say for example, if you have 32-bit virtual address space, then that means that we have got the processor view of the memory hierarchy. The processor is going to think that it has a 32-bit address space when in reality it's essentially just 30 bits or fewer bits. The addresses are going to go from 0 all the way to 2 raised to 32 minus 1 because we have 32 bits to access each particular virtual address location. And because it's a virtual space, we are able to arrange it in a very clean fashion. The size of that virtual address space is going to be in the gigabytes, several hundreds of gigabytes or even terabytes range. So for a programmer though, that's going to be, the programmer's view is going to be the same as a virtual address space. Very different from a physical address space. So the grand illusion by using this the concept of virtual memory is we are essentially mapping a small, messy, and fragmented physical address space that is essentially installed in the dynamic RAM. Two, we are able to map that or translate that into a virtual address space that is relatively large, it is clean, and that particular page mapping allows us to give that illusion. Um, why is the physical address space fragmented? Because all the frames don't have to correspond to the same program, and it doesn't have to be contiguous. So frame 0 could correspond to program 1, program 2, program 3. They could all, so it's going to turn out to be a fragmented physical address space. And it is going to be messy because the mapping is not going to be very straightforward. It could go in any which way. So by doing this, we create the illusion of a very big and clean virtual address space that we are showing on the right, but in reality we are using a small amount of physical dynamic RAM storage. Because we are introducing some new concepts and terminology here, let's try to compare and contrast. We are essentially having the same concepts. We are just essentially changing the terminology and slightly different implementation. So over here we have a comparison between a cache that we have seen in the previous set of lectures on memory, and on the right we have a comparison of terminology with the virtual memory. So for a cache, we were accessing the cache, and for virtual memory we need to look at the mapping. So we look at the page table, which has that mapping for each page number, what's the physical address or what is the disk address. A miss would mean like a page fault. So if the page is not listed in the page table, then it means that we have a page fault and we need to get the page from the hard disk to the dynamic RAM and then update the page table. So that essentially page fault. Miss rate for cache is going to be similar in concept to a page fault rate. So how many accesses to the page table resulted in having to access the hard drive, the fraction of them. A block, which is a collection of words in cache. Over here we have a page, which is a fixed length contiguous memory. We were using in a cache, we were using an offset with a block within a block. Over here in virtual memory, we are using bits to suggest the offset within a page. Cache is real. It's a pure hardware implementation. It is relatively very small and very close to the processor. A virtual memory system is a combination of an operating system, software, and CPU hardware. It is supposed to be very big. Alright, so these are some things we can compare between cache and virtual memory system. We will start talking about page tables, page faults, and the corresponding performance of virtual memory in the next lecture.